Hello everyone. We are students of Aerospace Engineering at UABC and our team is called South America. Throughout this video, we will explain the procedure that follow for the realization of this practice which is called Aerodynamic Coefficient of Airplane. And I will mention the objectives of the practice. First of all, is know the proper management of the wind tunnel throughout the practice. The second one is acquire the practical knowledge of the behavior of a system around the profiles and compare the results with the calculation of a drag, lift, forces for aircraft. And the last one is take several readings of the variation of practice in the measurements, manipulating the wind tunnel speed and the angular position of the profile, analyzing this way the interaction of the flow and a solid. We use this airplane to perform the analysis and data collection. We had to place a dipstick to hold the model fixedly without it having vibrations or any other type of inconvenience that will cause failures in the readings.
Due to the wings of our model were in contact with the rod, we had to use a sandpaper number 40 to remove material from the edge of the rod and thus avoid contact of the wings with it. When sanding, we place the nut and stick the plane to it from the center of mass. Before we start testing, the tunnel was placed in a diagonal position so that the exhaust air wouldn't be very close to the wall and not affect our readings. After this, we proceed to turn on the tunnel. We pull up the brake and press the power button. Then, the test zone was removed to place our model. We made sure that by adjusting the half-inch diameter rod to the fastener, the angle of the knob was in accordance with the plane's completely horizontal position.
Once this was done, we increased the velocity up to 36 meters per second as seen in the measurements. So we can obtain the data to analyze the plots and the behavior of the forces of lift, drag, and friction moment. We just need to connect a USB cable from the tunnel user interface to our laptop and press play. The angles that were used were minus 25, minus 20, minus 15, minus 10, minus 5, 0, 5, 10, 15, 20, and 25. We considered that 10 minutes per measurement was enough per test. When a measurement of a certain angle came to an end, the wind tunnel sometimes wasn't able to stabilize and put the forces on 0. So we had to press the reset button each time this happened and wait for it to stabilize. We saved the information that we gathered from each angle in Excel to make it easier for us to analyze the data.
we did a partial analysis, we can proceed with the post-procedure. We're going to analyze and graphic all the data that we got in the wind tunnel. The data we're seeing in this moment, we call it the raw forces. Since before making the graphics and analysis, the information we have to change the negative forces to positive and vice versa. And of course, we also have to calculate the average force with the respective angle of attack. This is because the wind tunnel doesn't give us according to the aircraft in 1 force per second. Then we have to calculate the area of the wind surface. Now that we know the velocity of the wind, that is in this case 26. This will be 2 out of the 3 constants to calculate the aerodynamic coefficients. The third one is the density, that we choose to use the one at sea level. But we will use them later, since first we will show us the graphics of the lift and drag how they behave. To know how they behave, we add a trend line, like you see in this video, where the lift acts like a linear line and the drag acts like a parabol. This means that every time the aircraft has a bigger angle of attack, there's going to be a better lift, until the angle of attack of 15 degrees. And closer to 0 degree, less drag there's going to be. As we can see, there's 2 tables here. One where you can see the drag and lift that had the aircraft, then the calculations we made with a simple formula of calculating the aerodynamic coefficients. If we graph these coefficients, the lines are going to be the same as the graphics of the respective forces. In this graphic, it's called the radius of coefficients. Also the efficiency, where it is very visible that the better efficiency of the lift and drag will be, and the angle of attack at 10 degrees. This graphic, the last one, is just a way to see the horizontal adds the lift coefficient, and in the vertical adds the drag coefficient. This also acts like a kind of parabol.
The expression of aerodynamic forces and moments in the form of aerodynamic coefficients is very important in aerodynamic studies and calculation, simplifying them considerably. The aerodynamic force acting on an airplane can attain values in the hundreds and thousands of kilonewtons. The same force acting on the model of this plane which is being tested in a wind tunnel will be tens of newtons, but the aerodynamic coefficients for the airplane and the model will be equal. We can conclude that the greater the angle of attack, the greater is support, while when its angle is 0, the lift is also, and this is because the greater the contact area in a region, the more fluid velocity there will be in that region, and the difference in pressure will generate the lift is phenomenon is created the difference of pressures in the area. As we know that each force acts backward resisting the forward movement of the aircraft through the air. Saying the above, we can conclude that due to that in the drag graph we have only negative values due to the contact area that the plane has with the current air. We can understand the drag. This means that when our profile is at an attack or attack equal to 0, the contact area of the airstream is minimal. Therefore, is the point where the dragon is almost 0 when there is an attack of angle of 20 or 25. There is a greater contact area. This means that the drag will be greater. In a few words, if there is a greater contact area, it causes a greater resistance to the air. Observation, it can be concluded that the wind tunnel doesn't have the best condition to work, and this may be due to a poor calibration, just as the air currents generated in the facilities affect our results. The latter improved with the implementation of a honeycomb after the noose, making the flow more stable.